Okay, good afternoon, colleague. Today, we want to look at rooted tree as an application to Runge-Kutta method. Now, our last class, we look at Runge-Kutta method. We derive some scheme using Taylor series expansion. But we want to look at the rooted tree or the rooted tree application to Runge-Kutta. Firstly, if we consider the differential equation, y prime equals f of y of t. That is, the first derivative of y is equals to f. If we differentiate this the second time, we are going to have y prime prime equals, if I differentiate this, since f of y is a function of t, then I'm going to use function of function to differentiate it. Then I have y prime into fy of t. If I differentiate y of t, I have y prime of t. Then if I substitute y prime of t, then I will have f prime of y of t, fy of t, which is the same thing as what? F prime f for the second derivative of the differential equation. The third derivative is also defined in this way. Then I will differentiate this twice and now have two function of function. Then at the end of the day, I'm going to have y f prime prime f prime plus f prime f. At the end of the day, I'm going to have f prime prime f plus y f prime f. Let's look at the fourth order derivative. If we look at the fourth order derivative, we have this. And then all these function, they will be representing the rooted tree, the tree. They are all tree. But let's just get the derivation first. How we come about those three. We are going to explain it. This is just normal differentiation of higher order. Then at the end of the day, the fourth derivative is going to give me y f prime prime f comma f plus f prime prime f prime f comma f plus f prime prime f prime f plus f prime prime f comma f plus f prime f prime. Those are the fourth order, the higher order of the differentiation. Let's now see the definition of those things. Fy of t, we denote it as f prime of y of t, we denote it as f prime, f prime prime of y of t, we denote it as f prime prime, and f prime 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 y of t, we denote it as f prime prime. Now, let's define some terminology used with rooted tree. The first one we are going to look at is vertex. When you say vertex, when we have a tree, there's something we have. The first vertex that we are going to have is what is called the root. Then the root is going to have different branches, and those branches will extend. Now we said a rooted tree has one vertex known as root. That is the starting point. It must have a root. Then the vertex are connected by several branches. Yes, we are going to have central branch or several branches connected to just one vertex, which is the root, the starting point of the tree. Then let's look at the second one. We have what is called leaf. A vertex that do not have a branch is called what? A leaf. Yes, we can have many roots, but the last root or the last point is what is called a leaf. We can have a root extend to a leaf. That leaf can still be a root extend to another leaf until we have a vertex that is not attached to any branch. Then that is called a leaf. Then we want to look at order. How are we going to get the order of a tree? The order of a tree is the number of vertices in the tree and is defined as the row. I used row to represent my order, which is equals to 1 plus summation from I equals to 1 to k mi, which is the multiple of the tree. In case we have the tree that is identical, the multiple, and what? The row of ti, that is that row of ti is the leaf. That is the leaf. We must break the tree down until we get to the last leaf, which is the point without what? Without branches. Now let's look at order of symmetry. The order of symmetry is defined as this. Is defined as this. This is what the multiplication summation of mi factorial. My m is still multiplicity of the tree, and this that is just the formula for symmetry of the tree. Now we also have another term which is known as what? Density. Density is defined as this. We have the epsilon equals the order, which is the order of the tree, times the multiplicity of the density raised to power mi. That is just the definition for density. We also look at what is called ordered set of a tree. We have ordered sets. We also have unordered sets. The ordered set of a tree is the number of ways in which we can label our tree. Yes, this tree, the audacity of the tree, the way it can label is called the order of the tree, and is defined as we use alpha of t to define my order, which is equals to the order factorial, that is the row factorial, divided by the density times the symmetry. That is, order set of a tree is defined as the order factorial divided by density times this order of symmetry. We also have the unordered set of a tree. The unordered set of a tree is also defined as the way of labeling with unordered sets, and is defined as the beta of t equals ordered factorial divided by the order of symmetry. That is the term using trees. Now let's now see another one is elementary differential. Elementary differentials are those our differential, like what we showed the other time to us. The first derivative of y prime, second derivative, third derivative, those are the elementary differential. That is, our tree is going to be break down to elementary differential. Now let's now see an application of those terminology, applying it to tree. The first tree, we are going to consider the following tree. The following tree are fourth order tree from 1 to 4th. Now we start from the first one, which is when we have dots. That is, we want to determine the parameters that we listed above. That is the order of the tree, the order of symmetry of the tree, density of the tree, the order set of the tree, unordered set of the tree, and the differential of the tree. We are going to take all these three one after the other. Let's just take one dot. As we see, one dot is just like saying it has just a leaf without root, or we said it is a root without leaf. Now, it means the order of this is just one because we don't have leaf, or we don't have root. We just say the leaf is what? Is 0. Then we are going to have the order to be equals to 1. That is why we have the order equals to 1. Also, our density, because we don't have any leaf, we cannot see any symmetry. Then our order of symmetry is also equals to 1. The same thing to our density is also equals to 1. Our ordered set is also equals to 1 factorial divided by 1 times 1, which is also 1. And our unordered set is also what? 1 factorial divided by 1, which is what? 1. Then the differential equation will just be ordinary f, because it's just a what? A leaf. Now let's look at when we have two dots. That is, we have a root and a leaf. Now our order of these three is going to be 1 plus, from the formula of the order, 1 plus summation I from 1 to k mi order of what? Of the leaf. 1 plus, there is no multiplicity, it's just one leaf. That is why we have 1 plus, and we don't have, aside that leaf, we don't have any other leaf. Then we say 1 plus 1 equals to 2. Then the order is 2. Let's look at order of symmetry. Order of symmetry, the same thing. We have just one leaf after the root. Then we say 1 factorial into the leaf is just 1 raised to power 1, then we have 1. Now let's look at density. Density is row times, that is, my row is the order. The order of these 3 is 2. We have 2 times, then we have 1 leaf. It means it's going to be 1 raised to power of the multiplicity. We don't have any multiplicity, it's just 1 raised to power 1. At the end of the day, the density of this 3 is going to be what? 2. Now, the other set of these 3 is going to be 2 factorial divided by 1 times 2, which is equals to 1. Unordered will be what? 2 factorial divided by, because unordered is ordered factorial divided by order symmetry, which is what? 2 factorial divided by 1, which is 2. And the differential coefficient is going to be, now we now have a root attached to a leaf. That is why we have f prime. If a root is attached to a leaf, then we have f prime. Then after that, we also have 1 leaf. That is why we have f prime f. Let's look at this tree again. Now, look at this tree now. We have a root attached to 2 different leaves. Then we can say the order of this is going to be 1 plus, the multiplicity is what? Is 2, because we have the same leaf attached to what? 1 root. Then we said 2 times, the 2 leaf is not attached to any other one. Then we say 1. Then at the end of it, we have 2 plus 1, which is 3. Then let's look at the order of symmetry. The order of symmetry, the multiplicity is 2. We said 2 factorial, and the leaf does not extend to anything. We said 1 raised to power 1, which is also 2. We also look at the density. The density is the order times, the order of this tree is 3 times. Now the tree has just leaf, 1 leaf. The leaf does not extend. That's why we have 1 raised to power. The multiplicity of the leaf is what? Is 2. That is why we have 3 times 1 raised to power 2, which is still 3. Now ordered set, we are going to have ordered set will be 3 factorial divided by 2 times 3, which is equals to 6 over 6, which is equals to 1. Also unordered, we are going to have 3 factorial divided by 2, which is 6 divided by 2, 3. And the differential coefficient is going to be this. Now, we have a leaf, we have a root attached to 2 different leaves. Then we are going to say, since it's just 1 leaf that is attached with just a leaf, but it's been in 2 places. That is why we have f prime into f comma f. That is the what? The differential coefficient for this tree. Now let's look at another tree. Look at this tree now. We want to get the order of this tree. Now, this tree, it has a root attached to another root, and that root is now attached to a leaf. Then it means we are going to consider from that root, from the starting point to the other root. We make the other root to be a leaf. That is why we have 1 plus. Now, we make the second one to be a root now, which is what? 1 plus, and the last root has no root. Then we have 1 plus 1 plus 1, which is 3. Now, let's look at order of symmetry. The multiplicity of this is 1. Starting from the root to leaf is just 1. But the second leaf will now turn to a root for the third leaf. Then we have 1 factorial, open bracket again, 1 factorial, 1 raised to power 1, all raised to power 1, which is still 1. Then we have our density to be the order of the tree, which is 3 times the tree has just 1. Okay, for the first one, we are going to have 1. Since it has 2. Okay, if you consider the first tree, then we have 3 as the order. Then if I consider the next root, that is the second one, then I'm going to have the order to be 2. Then if I consider the last one, I'm going to have the order to be 1. Then I will not have any, that is why I have 3 into 2 into 1 raised to power 2 equals to 3 times 2 times 1, which is 6. Let me explain this again. If you look at this tree, it has a root attached to a leaf, and that leaf also attached to another leaf. Then I can make my middle point to be another root. Now, if I'm considering the entire tree, then the order of this tree will be 3. Now, if I move to the middle one, then the order will reduce to 2. Then if I get to the other, I will not have the other. That is why I have 3 into 2 into 1. And if I multiply, I'm going to have 6. Now, the other symmetry. The other symmetry is going to be 3 factorial into 1 times 6, which is what? 6 over 6, which is equals to 1. Then I have unordered set is going to be ordered factorial, which is 3 factorial divided by the other symmetry, which is 1. I'm going to have 6 over 1. And the differential coefficient. Now, look at this. My first root is being connected to a leaf. That is why I have f prime. The second root is connected to a leaf again. I have f prime again. Then the last leaf does not connect to anything. That is why I have my f. Let's look at this also. Now, this is a root now connected to 3 different leaves. Then we can get the order. The order of it will just be 1 plus, since we just have one root, others are leaf. Then the leaf occur in 3 places. That is why we have the multiplicity to be 3 times. We don't have any other thing attached to those leaves. That is why we have 1 plus 3, which is equals to 4. Then we want to get the other symmetry. We are going to have this. Now, the multiplicity of the leaf is 3. That is why we have 3 factorial. Then we don't have any other thing attached to the leaf. That is why we have 1 raised to power of the multiplicity, which is 3. Then I have 3 factorial, which is 6. Then I want to get my density again. Density from the formula, I'm going to have the order of this tree is 4 into. Now, I don't have any root again. I will say it's 1. The multiplicity is 3. Then I have 4 times 1 raised to power of 3, which is still 4. Then I can get the ordered set. The ordered set will just be 4 factorial divided by 6 times 4, which is what? 24 over 24, which is equals to 1. Now, on ordered set, I'm going to have 4 factorial divided by 6, which is equals to 4. Now, the differential equation or differential coefficient is going to be, now this is a root attached to 3 different leaves. Then I'm going to have f prime 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 prime. Then I don't have the 3 leaf is not attached to anything. That is why I have f comma f f comma f. Each leaf is f, but root we have the what? The power. Now let's look at this also. The same thing to this. We have a root attached to another root, then that other root is now attached to 2 different leaves. Then we can, if you consider the first root that is attached to the leaf, they have 1 plus. Then if I consider the second root attached to 2 leaves, I have 1 plus. Now this is 2. Then I have multiplicity to be 2 into, I don't have any leaf again, I have 1. Then if I add everything together, I have 1 plus 3, which is 4. Now, ordered set, if I see the ordered set, then for the first one, I don't have any multiplicity, then I have just 1 factorial. Now, if I open bracket for the second one, I have 2 multiplicity because I have 2 leaf. That is why I have 2 factorial, then I have 1. If I perform the operation, I have 2 to be my answer. Now, let's look at the density. The order of this tree is 4 when I consider the roots from the down. Then I move up, I move to another root. Then the order of the other tree now is now 3. Then I don't have any tree again, I have just leaf, and I have 1, and I have the multiplicity to be 2. That is why I have 1 raised to power 2. At the end of the day, I have 4 times 3 times 1 raised to power 2, which is 12. Then ordered set is going to be the order factorial divided by order symmetry times density. Then alpha factorial divided by 2 times 12, which is what? 24 over 24, which is equals to 1. Then I have my unordered set to be equals to 4 factorial divided by 2, which is 12. Then my differential coefficient. Now, differential coefficient. The first one, I start from a root, I move to another root. That is why f prime. Then this other root now have to leave. That's why I have f prime prime. Then the leave, I have f comma f. Now, I'm going to show a table that will summarize the 4 ordered of what? Tree. 4 order root of a tree. 4 order condition of a tree that will summarize all the calculation that I show above. Now, let's look at the summary. We have the arrow there is standing for the order. This is standing for the order density, order symmetry, the symmetry. This is standing for density. Alpha is standing for the ordered set, beta is standing for an ordered set, and ft is standing for differential coefficient. Now, we want to look at how to apply all these things to Taylor series expansion. Remember our Taylor series expansion. Now, before that, I want to consider something. Now, there's something called elementary coefficient vector. The elementary coefficient, I have elementary coefficient vector defined in this way. That is defined in this manner. Then it can also be defined in this, where aij and epsilon j of tk. Then this is now defined as this. Now there is the linkage between this and RK method is the RK method is of that P if summation from I to x is the stage, bi epsilon I of t equals 1 over density. 1 over density. This is just the link between the rooted tree and the Runge-Kutta method, and this is what is called order condition for the tree. Now let's now see from Taylor series expansion. Generally, we know Taylor series expansion of this is the of y of t plus 1 is defined as this: yt plus h y prime of t plus h squared divided by 2 factorial y prime prime tn plus h cubed over 3 factorial y prime prime tn plus h4 divided by 4 factorial y prime 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 of t, so on. Now, if I substitute those, okay, before that, the exact solution in terms of the rooted tree is defined as this. The exact solution is defined as yt of those order expansion I will represent as summation alpha t, and my alpha is the word ordered set over h raised to power p. My row is the order of the tree divided by the row factorial f of t. My f of t is the differential coefficient y of tn. This is the exact solution of the method. Then from my relationship between of ordered set, we know that the ordered set is defined as ordered factorial, that's row factorial, divided by density times order of symmetry. Then if I substitute that into my equation 1, then I'm going to have the exact solution is going to reduce to ytn plus summation h raised to power of the order divided by the density times order of symmetry times f of t, which is my differential coefficient y of tn. The same thing, if I can also define it in terms of unordered set. The one I defined up is ordered set. I can also define it in terms of what? Unordered set. If I define it in terms of unordered set, I'm going to have this. Then if I relate we now know that the ordered set beta, the unordered set beta is what is equals to order of the tree divided by the symmetry of the tree. If I substitute it, I'm going to have this. And if I compare my equation 3 and equation 4, I'm going to see that my epsilon of t is equals to 1 divided by density. Then in one of the formula, the theorem I showed that link rooted tree with Runge-Kutta method have something of this. It means I can replace that with this, with alpha of t. Now let's see application of the rooted tree to Runge-Kutta. We are going to look at the test question. The test question number 2. Using the rooted tree list, list the third order condition of the two-stage Runge-Kutta method. Hence, using the Fassan property and the simplify assumption, express the coefficient of the method using Bouchard tableau, using C1 equals alpha, C2 equals beta as free parameter. Full stop. Consequently, obtain the implicit Runge-Kutta method with the choice of alpha equals 1 over 3 and beta equals 1. Now, let's see how we are going to solve this problem. All the sentences are very, very important. The question said we should use rooted tree. We must not use Taylor series expansion. We must use rooted tree. Now, if I apply rooted tree, I want to use the third order condition, then I must list all the tree that has third order condition, that is from 1 point to 2 point to the 3 point. All three other conditions, I must list them out, and after that I'm going to use the Fassan condition. Let's look at the solution together. The first solution, the other condition for Runge-Kutta, like the theorem I quoted, is defined in this form, where epsilon is the density of the tree and it is defined as this. Is defined as this. I've given us this formula before. Then we are going to get those epsilon I for each tree. So for each tree. Now, for the first tree, which is just ordinary point, I've said is what is 1, because it has no tree. It's just it has no leaf. It's just a root. Then it's 1. Then if I substitute it into my equation 1, I will now see that. And if you see, the density of this tree that we calculated the other time is just 1. Then if I substitute everything into equation 1, and my problem is also to what is two-stage Runge-Kutta. That is why my S is going to be 2. I'm working with two-stage. My S is going to be 2. Then I'm going to have summation I from I equals to 1 to 2. Then BI. Then my epsilon IT is equals to 1. Then if I put that, I'm going to have equals, my density is 1 over 1. That is why I have the 1. Then if I expand the epsilon, the summation, I'm going to have B1 plus B2 equals 1. That is for a dot tree or one tree, a tree that has just root without leaf, or we can say it has just a leaf without root. Now let's see the second one. When we have this, that is root attached to just a leaf, then I can say what? My expansion, if I calculate this, I have from 1, that is just the one expansion. Then the other, it means my epsilon j will just be what? Just 1, because it's just a leaf that it has. That is why if I substitute it, I'm going to have 1. And that 1 will now be what? Summation j equals to 1 x aij. That is what the will give me. And if you remember from our Bouchard tableau, summation aij is equals to what? Ci. Then if I substitute it into equation 1, I'm going to have bi ci Now, my epsilon I is now Ci. That equals 1 over the density of this tree is 2. That is why I have 1 over 2. Then if I expand my summation, I'm going to have B1 C1 plus B2 C2 equals 1 over 2. Now, let's look at the third order condition. Third order condition is of 2, but I will consider the first one first. The first one, when we have a root with 2 different leaves, then it means my product summation will just be what? 2, because I have 2 leaves. That is why multiplicity is 2. That's why I have 2. Then I have Aij, this. I will multiply it in 2 places. That is what it means. Then at the end of the day, I have summation j equals to 1 to Aij all square. And my summation Aij is what? Is Ci. Then I have Ci square. Then if I substitute that into my equation 1, I have summation from I equals to 1 to 2 bi Ci square equals the density of this tree is 3. That is why we have 1 over 3. Then if I expand it, then I have b1 C1 square plus b2 C2 square. Sorry, is C2 square. Now let's look at the second, third order condition, the order 3. Then I have, now this one has 2 different roots. Yes, if I consider the first root, I'm going to have this another 3 again, because I'm going to have another root. That is why I have this. But if I do the summation, I'm going to have Aij with what? Cj. That is what this tree is going to give me if I apply that method. Then if I substitute that into my equation 1, and the density of this tree is also equals to 6. We have calculated it before. Then if I substitute it, I have summation from I equals to 1 to 2 bi Aij Cj equals 1 over 6. Then if I expand it, since I'm now having two variable, or I can say 2 terms, I have I and I have j. Then I keep one variable and I keep one constant and I vary the other one. If my I is constant, then I have B1, A1, 1, C1 plus A12, C2. That is when I keep my what? My I constant for 1. If my I now vary now 2, I have B2, the second equals A21 C1 plus A22 C2 equals 1 over 6. This is what the expansion of this give me. Then I have those equation from 3 above 3, 4, 5, 6. Then I will solve those equations. But before I solve, I need to represent it in a Bouchard tableau. And as I said, if you are not told that is an explicit, you didn't specify, then you take your Bouchard tableau to be an implicit. Then I draw the Bouchard tableau. Then I have this for implicit, the Bouchard tableau for second stage implicit Runge-Kutta method is defined in this way. But in the question, we are given a condition. The condition is we should apply Fasan. That Fasan means the first to be Fasan means first to last. That is, I'm going to change A21, A22 to B1, B2. Why are we doing this? We want to make the system to be easy so that it can be easily solved. Without that, we may find it difficult to solve the systems of equation. Now, the systems of equation we have over there, we have equation 3, which is defined as B1 plus B2 equals 1. We have equation 4, which is defined as B1 C1 plus B2 C2 equals 1 over 2. We have equation 5 that defined as B1 C1 square plus B2 C2 square equals 1 over 3. And we have equation 6 that also defined as B1 into A11 C1 plus A12 C2 plus B2 into A21 C1 plus A22 C2 equals 1 over 6. Now, we are given some condition in the question, or we are given some parameter. We are given two parameter from the question. The parameter, we are given C1 to be equals to alpha and C2 to be equals to beta. Then if I substitute this into my equation 3 to 6, then I can say my B1 alpha 1, that is, I'm going to replace C1 with alpha, plus B2 beta, that is, I'm going to replace C2 with beta, equals 1 over 2. Call that equation 7. And I'm going to do the same thing to my equation 5. Then I have B1 alpha square plus B2 beta square equals 1 over 3. And I call that equation 8. And also, if I do it to equation 6, I'm going to have B1 equals A11 alpha plus A12 beta plus B2 into A21 alpha plus A22 beta equals 1 over 6. Then I want to solve this question. Then if I solve this question, okay, from the versal condition that I said the other time, I'm going to replace that. I have my A21 has turned to B1 and A22 has turned to B2. Then we are also given some other conditions. If alpha is equals to 1 over 3 and beta is equals to 1, all these parameters given is just to make the system to be easily solved, or the equation to be easily solved. Now, if I substitute alpha equals 1 over 3 and beta equals to 1 to my equation 7, 8, 9, I'm going to have something of this. I'm going to have equation 7 to be equals to 1 over 3 B1 plus B2 equals 1 over 2, and equation 8 is going to be 1 over 9 B1 plus B2 equals 1 over 3. Then if I solve these two equations simultaneously, I have my B1 to be equals to 3 over 4 and B2 to be equals to 1 over 4. Then if I substitute B1 and B2 into equation 6 or equation 9 over there, and also I know that my A21 is now B from the versal condition, and A22 is B, A21 is B1 and A22 is B2. Then my equation 6 then will be in this form. Then I will substitute those value of B1, B2, then I have this. If I substitute this, at the end of the day, my equation, the only variable I'm going to have in this equation will just be A11 plus A12. Then I know that what is going to give me A11 plus 3A12 equals 1 over 6. Then I call that equation 10. And from, we also know that C1 is equals to A11 plus A12 from our Butcher tableau. Then I call that, and my C1, which is equals to alpha, which is equals to 1 over 3. I call this equation 11. Then if I solve equation 10 and equation 11 together simultaneously, then I will see that my A11 is equals to 5 over 12 and A12 is equals to minus 1 over 12. At the end of the day, my new Butcher tableau for this problem will now be this, which is what they asked us to do. I think from here I'll be able to make justice to the question. Let us try and practice the question. We are going to end the class now.